Okay, our next topic is linear programming. Okay, linear programming it's a mathematical process and takes into account the variables and restrictions and requirements of a certain situation, whatever it might be, and then it comes up with the best solution from all of that. Okay, so maybe a manufacturing thing, and you got a whole bunch of different variables, time that your workers are available, etc., the amount of materials available, the cost of the materials, how much it costs you to pay your workers and all that sort of thing, and then the requirements obviously would be to maximise your profit. Alright, so it does those sorts of things. So basically what we need to know first of all though is we need to look at linear inequations. Okay, and so linear inequations are what we use in linear programming to find to maximise or minimise or whatever. Okay, so there's a few things that we need to look at, and I'll just do that through some examples rather than giving you a whole bunch of definitions, which I could do. So let's have a look at an example. Let's spell it properly. Oops. There we go. Sketch the graph of, say, y is greater than or equal to 0. Let's take something simple to start with. Okay, so it goes on our Cartesian plane, of course. There's our Cartesian plane. Y is greater than or equal to 0. Well, y is equal to 0 here, along that line there. And y is greater than 0 up the top here, or above at that line. Now, with the linear programming, what we do is we do kind of the opposite than to highlighting the bit we want. What we actually do is we cross out the other part. And once we get further down and we start putting a few of these on the one axis, the reason it's kind of become a bit obvious that we cross out what we don't want. Because if you've got 4 or 5 of these things and you're shading in what you do want, it's very difficult to see where it all overlaps. But if you cross out what you don't want, then you've got 4 or 5 things and you've got a blank spot, then it's easier to pick up. Alright, so that's simply what that one would look like. Now, some of these symbols, like this one here, we've got greater than or equal to, less than or equal to. For them, we use a solid line, as I've done with that red line there. But if we just had greater than or less than, then we'd use a broken line. Okay, where that broken line's indicating that it's up to, but not including. So an example of, say, something like that might be if we're sketching, say, x is greater than 6, for example. So on our Cartesian plane, there it is, x and y. 2, 4, 6, 8. Like so. X equals 6 along that line there. Now, because it's greater than and not equals to as well, then the line that we need to put there needs to be a dashed line. So what that indicates is that up to, but not including, 6 is required. What do we require? We require x greater than 6, so we require up here. So what we do is, remember, we cross out what we don't want. So we don't want that bit over there. Right, now, what I didn't put before that I should have put, you need to have a key. So I've got a box there, region required. So in my previous example I forgot to put that. But you should always put that, just in case. And then of course if you make a bit of a mistake you can always swap it around. Alright, so there's that. Of course we can have more complicated questions than that, ones that involve both x and y. So let's have a sketch of, say, negative y plus 3 is less than 5. Okay. Bunch of different ways that we can look at this. So negative y is less than, if we are taking 3 from both sides, negative y is less than 2, and then if we then divide both sides by negative 1, but when we do that we've got to swap this around. So that becomes greater than, so y is greater than negative 2. Alright, x, y, 1, 2, 3, 4, negative. Okay, it's greater than, so it's, the line's not included, so we need to have a dashed line there. We want the greater than, so we need to cross out the other bit. So our region required is therefore a bit above that line. Alright, so none of them so far have had x and y, so let's do an example where x and y are involved. And so this one's y minus 4x is less than or equal to 8. Okay, so y minus 4x is less than or equal to 8. The easiest thing for us to just start with is y minus 4x equals 8. So let's look at where it equals at the moment, and then we'll come back and look where it's less than or equal to. So y-intercept, x equals 0, so y would be 8, I believe, and x-intercepts, y equals 0, and so x would be, I believe, minus 2. So what we have then is we have a graph that looks like so. 2, 4, 6, 8, 2, 4, 2, 4. Okay, so our y-intercept is 8, our x-intercept's minus 2, it's equals as well, so we need solid line. So there we go. Okay, now we need to know which side of the line it is that we're looking at. One of the ways we can do that is by substituting a point, choosing a point somewhere, and if you can, the origin's a great point to choose, because if we choose 0, 0, it just makes the calculations easier. And if we put it in, we get 0 minus 4 times 0 less than or equal to 8. So you get 0 less than or equal to 8. Well, yes it is. 0 is less than or equal to 8. It's in fact the less than part, not the equals part. So that point that we've chosen satisfies that equation, so that means that that is in the region. So that's in the region. So if that's in the region, we want to keep that, and we want to cross out the other side. So we want to cross out the side of the line that doesn't include 0, 0. And so the blank part there is the region required. Alright, so exercise 11A, which is in problem set number 1, involves you sketching these inequalities. Okay.